Imagine a world where you can see your future health, not just diagnose current disease, but see and project your health profile in the future. Is it hype? Is it real? We'll talk about this today. Welcome to the AI Brothers podcast. We are two brothers who have been discussing technology since we were kids and have decided to include you in these conversations.
We will cut through the noise to bring you data and research on the latest developments on AI. We are not interested in hype. We bring you the signal to keep you on top of this technological and this industrial revolution.
Because AI will permeate everything and be everywhere, initially as a layer on top of existing systems, and then become in itself the operating system.
Today's topic feels like sci-fi, even for a techno-optimist like me. Predicting diseases decades in advance. It's amazing.
Well, the research is here, and it is impressive. I feel like we started this podcast to look into the AI research, to uncover what's real and what's hype. And at least for me, I was expecting to uncover a lot of hype.
And now you are realizing you were wrong. Welcome to the techno-optimism, huh?
Well, I think I'll still keep my skepticism. I did train in France, so I carry a strong bias against opinions masquerading as fact. The famous quote from Montaigne that said, "A man's plague is his opinion."
Sounds very boring. Thankfully, today we talk about some exciting advances in AI and healthcare. Probably one of the most important applications of AI. In a research published in the prestigious journal Nature, titled Learning the Natural History of Human Disease with Generative Transformers, authors shows that a modified GPT-2 can predict future disease from a person healthcare history.
Yeah. So this work is from a team at the European Bioinformatics Institute, based in Cambridge and Heidelberg, Germany. The paper is open access, so folks can access it. But first, let's set the scene here. So the big problem in healthcare is to predict broad outcomes. So we have tests and diagnostic tools to predict the outcome of a single disease. But when you talk about healthcare, you talk about a complex issue where multiple factors come together to drive someone's health. So the context of health and the evolution over time is a very difficult problem. So recently there were some machine learning algorithms trying to do it, but even they failed to predict outcome from a complex input.
Okay, the problem is to personalize the prediction to every individual and to do it at a reasonable cost. The core idea in this paper is that the same LLMs can predict the next word or token when trained enough on data. They should be able to predict diseases if trained on large health data.
Well, that's exactly it. And it seems like a brilliant, simple idea, but they had to do a few modifications to the architecture to make it work. So first of all, they represented a human's health history in a tokenized manner. So they converted all the disease into tokens, and they made sure to fill the empty spaces with no event label, so that the algorithm can have a continuous read. And then based on this representation, they trained the model on the UK Biobank. So for people who are not familiar with the UK Biobank, it's really a treasure for a lot of these data learning algorithm. So it has the anonymized data from hundreds of thousands of people, and has the health history of these people. It has, information regarding their health and the progression of their diseases. And actually a subset of this data is multimodal data, where it contains genomics, it contains nutrition data, it contains imaging data. So the way they trained the model is they took this database and they split it into various chunks. So the big chunk was used for training, which is 80% of the records, around 400,000 patients. And they use the rest for validation of the model and then later on for the testing of the model. So after this training, they also use the same sort of, after training the model, they later tested it on another health database, which is the database from Denmark. And we will talk about it later to talk about how this model performed.
So let's talk about the model. They started with the open source GPT-2 architecture. This model is a small model. They can run on smaller machines. On this architecture, they made some changes. First, GPT has a positional encoding, meaning that GPT normally marks each word with the position, first, second, third, etc. Here, instead of position, they marked each medical event with the real age that in which it happened. Second, normal GPT just predict the probability of the next word or token. Here they added a second output so that the model predicts how long until the next event happens using a simple timing formula. Third, GPT normally can only look at earlier events, not future ones. In the modified version, they made it to ignore events that happened at the exact same time. They call this new Delphi model. They showed that Delphi followed scaling laws, with the model getting better up to 2 million parameters.
Well, and these scaling laws are sort of typical in the AI training. So it's good to see that it also applied to health data. So after explaining sort of the how the architecture was designed, let's talk about how it actually performed. So, and this is really some impressive results. So first of all, they just took the model and let it model the disease trajectory. So here there's no prediction, just modeling the disease from the text. And you can see, we will put some graphs, and then you can see from the graphs that they had a pretty good modeling of the disease histories just from reading the text. And you don't need to be a doctor to just see that intuitively the results make sense. So, for instance, chickenpox peaks for children, for instance, and then you have breast cancer that is mostly affecting women, and then you can see sort of like all these disease history. Alzheimer tend to be later in life. So just from reading the text, the model is able to reproduce these trajectories. And not only does it reproduce these trajectories, it's also correlate very well with the real data. And in supplementary figure, they show this really nice correlation between the observed rate and the model rate, and this projection is very stable over time. This correlation, is very stable over time.
After demonstrating that the model works, they went to actual prediction. As input, they used individuals' health information up to 60 years and asked it to simulate health trajectory beyond that. Here again, they show a real good correlation between the simulation and the real data. The correlation is also very stable over time, meaning they can predict diseases up to 10 or even 20 years. The other impressive feature of this model is that it enables interpretation and gives indication on some level of causality. They show how diseases cluster together, like how diabetes clusters with the eyes diseases. They also show different factors affects the risk of a disease or even death. They show the example of pancreatic cancer, where stomach issues and liver diseases increase the rate of pancreatic cancer.
This to me is really just incredible, that you're able to get these results directly just from training on health data. And the way they sort of define the correctness of the model is by the area under the curve on a probability curve. So if the area under the curve of the model follows the area under the curve of the real observed data, they can define this to be strongly correlated. And then they took this model, and as we said initially, they applied it on data from the Danish healthcare database. And then again, it's just impressive how the AUC of prediction works very well for the Danish database. So the model that was trained on UK healthcare, when you input Danish healthcare, it still gets a very strong correlation.
I see the opportunities. If you can get this type of quality result from just diagnostic data, imagine all the things that you can get from integrating genetic data, lifestyle data, and more. Plus, they used GPT-2 architecture. What would happen if they used an even more advanced model like, I don't know, Kimi K2, the one that we discussed last week? We are talking about something potentially new and personalized and predictive, in medicine. This is incredible.
Yeah, absolutely. I mean, just to talk about the limitation, and in fairness to them, they did mention the limitation and they talked about them. So the first limitation that they mentioned is the fact that the healthcare data is from the UK biobank, so it's more of a Northern European groups, and even within the UK population, the people who volunteer to go into this data bank tend to be more affluent, more educated groups. So there is a bias in that source data. They also talk about how the data is recorded, and there are differences if the data was recorded in a hospital environment versus a general practice. The other limitation that they didn't mention, but I thought was quite important, is the size of the input relative to the output. So they needed about 60 years of health data so that they can predict the last two decades. I think it would be interesting to see how these models would perform if you would input just 30 or 40 years of data. But if you think about the opportunities that you just mentioned, it is very impressive. The potential for multimodal AI in healthcare, built on the technologies like Delphi that we discussed today, is tremendous. The ability to predict future outcome could change the healthcare system and make it so efficient. I also think this type of technology should be in the radar of countries in the Middle East who are heavily investing in their healthcare infrastructure and trying to build it from the ground up to be very different. Because here you really have the opportunity to create a system that is truly healthcare, caring about keeping people healthy and not disease care.
I agree. That would be an example of AI moving beyond a lawyer on top of existing system to become something like a new operating system,
Yes, and actually I was also thinking about something else, that actually as these models are evolving, maybe it's time for every one of us to start recording their own health history so that they are able to run these models themselves. So if you take the record of your own sort of modification, changes in weight, changes in health, changes in diet, and keep recording that, one day the models are going to be so good that even if you fill, let's say, 40 years of this multimodal data, it can tell you what's going to happen in the next 10 years of your health. And I think that is something super impressive. Well, I think that's our episode for today. We talk about the future of healthcare using AI. Thank you for listening. please subscribe, comment. We always love a good discussion, and we wish you a safe and productive day.